Hello everyone, this is Ruai PCB, your trusted PCB partner. Today we will introduce the design of power and ground networks on double layer boards, including trace width, spacing and current handling. After completing an excellent ground plane design, the next key step is to properly handle the power and ground networks. This is not just about simply connecting the traces, but about ensuring that the circuit receives a stable and clean power supply and can operate safely and reliably under various loads. The core lies in two aspects. The trace width must be able to carry the current, and the spacing must be able to isolate the voltage. How do you choose the appropriate power and ground traces based on the current? The fundamental principle is that the current determines the trace width. The conductors in a circuit have resistance, and when current flows through them, heat is generated according to Joule's law. If the conductor is too thin relative to the current, it will lead to two serious problems. First, overheating and damage. Excessive current can cause the temperature of the conductor to rise sharply, which may result in PCB delamination or bubbling in mild cases, and in severe cases directly burn out the conductor, causing an open circuit. Second, significant voltage drop. According to Ohm's law, V equals IR. Even a very small resistance can produce a non-negligible voltage drop when the current is large. For example, if a 5V power supply passes through an unsuitable thin wire and reaches the chip pin with only a little over 4V left, this is enough to cause the chip to malfunction or fail to start. So how do you choose the appropriate trace width? One way is the rule of thumb, which is suitable for lower currents and quick calculations. For most hobbyists and low power input circuits, you can remember a safe and conservative rule of thumb. 1 ampere of current corresponds to 1 millimeter of trace width. This rule is based on the condition of standard 1-ounce copper thickness with very little temperature rise and is sufficient for the vast majority of situations. The second method is precise calculation. According to IPC 2221 and 2152 standards, in commercial products or circuits with high reliability requirements, you need to use industry standard precise calculations. The IPC standards provide a set of standard formulas that take into account several factors such as current magnitude, allowable temperature rise, copper thickness, trace location, and so on. Nowadays, most PCB software also provides some calculation formulas. And then there's also the method of looking up tables. Here I have a temperature rise table, and I usually choose this method because it's relatively simple. At the top are the allowable temperature rises, 10 degrees, 20 degrees, 30 degrees. Generally, we pick a middle value, 20 or 30 degrees are both acceptable. This row here shows the copper thickness. Most of our PCBs use 1-ounce copper thickness, which is this value in the middle. And below that are the current and trace width. We can see there are two units. If we use millimeters as the standard and take 20 degrees as the reference, if I want to carry 3.6 amps, the width must be 1.27. Let's look at our PCB. Using this trace as a reference, we can see it's already labeled here. The output is 54 volts, 3 amps. So what is the width of this trace? I've set the trace width to 2 millimeters. Let's check the table again to see if 2 millimeters is appropriate. Using 20 degrees as the reference, with 1-ounce copper thickness and a current of 3 amps, we can look at this table. When the width reaches 1.27, it's enough to handle 3.6 amps. When the width is 1.9, it can handle 4.5 amps, and at a 10-degree temperature rise, it can also handle 3.5 amps. This means that with my settings, under full load, the current can pass through and the temperature rise is less than 10 degrees, so this design is reasonable. So you can see that there are many thick traces present. Next, we can also look at the battery section. This is the battery section. I use the copper pour method for the layout here because the current is even higher in this area. The width here has already reached. Let's take a look at how wide it is. The width is 17 millimeters, which means it can carry a very large current. Why is that? Because this is a boost converter board. It boosts the voltage from 4 batteries, 12 volts, up to 50 to 54 volts at 3 amps, which is 150 watts. So at this position, the current it carries is about 10 amps. That's why the trace width here is quite large. As for the ground line, if the entire bottom layer is already covered with copper as the ground plane, then its width is essentially unlimited and its current carrying capacity is very strong, so there's no need to worry. The trace width here mainly refers to the top layer power lines and those that can't be connected using the ground plane. Just like in my case here, mainly the top layer power lines and the connecting wires between these batteries can't use the ground plane. They can't use the ground plane for these connections. Minimum spacing between power and ground lines. The core principle is that voltage determines the spacing. The spacing between conductors is to prevent short circuits or arc breakdowns between different electrical networks. The main factor determining spacing is the voltage between two conductors. The higher the voltage, the greater the risk of air or PCB material breakdown, so a larger safety distance is required. So how do we set a safe spacing? Standard settings for low voltage circuits. For the vast majority of digital and analog circuits, the operating voltage is very low, typically 3.3V, 5V, 12V, or 24V. In this case, the main consideration is actually the PCB manufacturing process. The standard safety spacing is 8mm or 10mm. This spacing is much greater than the electrical safety distance required at low voltage, and it is a very common process value that can be achieved by the vast majority of PCB manufacturers. Setting the default rule in the design software to this value can effectively balance safety spacing, safety, and manufacturability. Just like with our PCB here, you can see that since the highest voltage is only 12V, a safety spacing of 10mm is sufficient to meet safety requirements. The main point is that if the PCB manufacturer has to make the spacing any smaller, it will increase the cost. Strict requirements for high voltage use. When high voltage is involved in the circuit, usually referring to voltages above 48V, strict safety standards must be followed. Generally, for 100V DC, at least 0.4 mm of spacing is required, while 500V requires 2.5 mm. So when high voltage input is involved, the safety spacing needs to be increased. Alright, that's all for today's content. If you enjoyed this video, please subscribe to my channel for more videos. Thank you everyone.